So this time we're going to play more with the concept of distance. And there's 3 more ways of doing this. And we talked about understanding the size of these stars and understanding the mass of them. Today we're going to figure out how do we actually reach them, and how do we reach out and measure these distances, and how do we do it for star systems other than these nice binary systems, which are wonderful when we have access to them. But if you look at these maps that we're generating, we have these very precise distance maps, and some of these are reaching quite a distance. This is actually our local region. This isn't too bad, but we're measuring distances to other galaxies. How's that even close to possible? So we're going to talk about the concept of distance itself, which might strike you as a little odd because you probably think that you have a grip on it. You probably don't. So we're going to talk about what that unit actually means. We're going to talk about light a little bit and different ways of measuring distance through light. There's a couple. And then we'll get into variable stars, which is pretty cool. This is how we essentially make our measurements, is understanding this particular class of stars that are expanding and contracting, right? They're pulsating. And the dynamics of that pulsation allows us to make a clock out of them, essentially. And if we understand that the same sort of star, which is our clock nearby, is also over in a galaxy far away, then we can make some deductions and some comparisons and actually understand how far away it is, right? Just like if I took a flashlight and I knew it was the same flashlight, but I went to the other side of the room and I took a camera, it would appear dimmer, right? But I would still know that it had the same characteristics as that other flashlight. And so through the inverse square law, right, light falls off with an inverse square. It radiates in all directions. So those radiations are going to be thinned out at a distance. And we can take that and convert it back and understand the distance. This is pretty cool. So before I get into all of that, somebody asked me last time, which is a freaking great question, what this alpha term was in the Stefan-Boltzmann relationship. Who was that? Yes, awesome. And I think that I gave you I think I gave you more or less the right answer, but I didn't have a lot of confidence about it. So remember, the Stefan-Boltzmann relationship is really important because it allows us to take the whole energy flux of a black body and to determine the whole energy flux of a black body just from the temperature, okay? So that means that how hot something's glowing, how hot a light bulb is, will tell us how much power it's giving out, what its wattage is, essentially, right? And we call this luminosity, absolute luminosity. But it's the same concept as energy flux or power, I think is a good way to think about it. Okay, so the Stefan-Boltzmann relationship that I threw on the board last week actually integrated it for the surface area of a sphere, because you want to know what the total power output is, not just at a point, but over the surface area of a star. And so this sigma is just, like I said before, it's a constant of proportionality which tells you how this scales. And this sigma incorporates a bunch of different other universal constants into it, so it's kind of a super constant. And you keep seeing these constants over and over again in physical equations as you look through them, right? There's the Boltzmann constant, there's the spring constant. They are always a measure of some particular material properties of the system. And in this case, Boltzmann writes that the sigma represents the total intensity radiated over all wavelengths increases as temperature increases, and that this is the proportionality scaling factor, which specifies exactly how it does that. So it's just a number. That's what it is. It's a number that tells you that the energy flux is, yes, it's proportional to temperature, the 4th power of temperature, but it's not exactly equal to it. It's only proportional to it. So proportionality has to be scaled. Maybe it's half of that value or a third or something. I'm not sure what the exact value of sigma is, but it's a number. Anyways, I wanted to cover that. Okay. Let's review really quickly what we did last time. So we talked about these spectroscopic binaries first, which was the ideas that came down from Newton and Kepler. Basically, if we know the period of the way that these binary pairs are orbiting one another, that we can We can pull out the speed from that. We can pull out the span of the orbit, and from that we get mass, and then we can triangulate, maybe we can triangulate distance in a best case scenario. But we didn't play too much with the distance calculation before. We'll do that today. We also talked about eclipsing binaries, which is a really special case scenario where the stars are perfectly lined up in front of you, and so you can actually watch the time it takes for one to disappear behind the other. You basically do this distance or you do this time speed translation, and you can pull out the size of that star as it disappears. Was there any questions from the last lecture about this? I know it was super technical and very fast, and I apologize for that, but we got to get on to the fun storytelling parts of this course. It's not meant to be a brutal astrophysics calculation fest. Yeah, okay. I got a thumbs up from the back. Yeah, more of the stories. I agree. You know, if any of you end up going into astronomy or astrophysics, you'll get plenty of time crunching numbers, so you won't have a lot of time for the history and the background and the imaginative processes, so we'll try to really play on that more. A lot of these speeds, by the way, depend on the Doppler effect, right? I want to make sure that you guys really understand that as well. So just to review, the concept of the Doppler effect is that, you know, waves, when they're emitted from a point source in any material, right? It's much easier to think about this as sound, but ultimately light behaves the same way. There's going to be regions of impulse and regions of relaxation, right? And I think that thinking about light this way is probably the right way to think about light. And the thing is, if these waves are being emitted in all directions, as you approach one of them, if you run towards it, you're going to encounter more of those wave crests per unit time than if you ran away from them, right? And so you can use this effect to see how the wavelength, the apparent wavelength that you're seeing as you move towards it or away from it, is changing. And when the wavelength goes down in sound, we would say, well, it's a lower tone, right? If it goes up, it's a higher tone, right? There's more waves per unit time. But in light, they're colors. And this is a little tricky to wrap your head around. But the bluer colors are faster. They're shorter wavelengths. The redder are longer, right? They're equivalent to the bass tones, right? So the reds you can think of as bass. The blues you can think of as treble. And so you have the same effect, and it allows you to gauge the speed of things because you can separate that out using some very simple arithmetic. Yes? Ooh. Yes. Yeah. Exactly. Yeah, that's a good point. I'm not sure about what wavelength this is in, so the way that they'll do this is they'll have filters that separate out each one of the wavelengths, right? And it's not something you can see with your eye, usually. And so I imagine this is just one filter length. And I'm not sure that you can see it getting redder or whatever, but usually they'll separate out the channels. And each one of the thing about redshift, particularly Doppler redshift, actually just the concept of redshift, when you hear that, what you're talking about is all of the wavelengths shifting a little bit towards the redder end of the spectrum, right? You're not talking about a single wavelength being shifted, right? And so there's a lot of confusion about this because there's all sorts of processes that will make light seem redder, but they won't affect the blue ones. They'll just screen them out or something like that. So when we get to, I think next week or soon, we're going to be talking about interstellar dust and all these processes that mess with our ability to see what's truly happening. And those come down to filtering processes, which is different than an overall shift. The Doppler process is a red shift. And so that's a highly confused concept. And yeah, we'll talk more about redshift when we get to cosmology too, because that turns out to be a super important pillar of our standard cosmology in Western science right now. Okay, questions? Good? All right, so we got to talk a little bit about space. Come on. Oh, we'll use the computer. So space is a terribly confused concept. And you have to start to really ask yourself what this word means, and moreover, if this can lead us to understanding what it is we're actually trying to measure in the first place. This basic law, which I'm trying to illustrate for you, is at the heart of everything that we're going to do today, which is an idea that was set forth a long time ago. So this was this is traditionally understood as the Pythagorean relationship, Pythagorean hypothesis. You probably learned it in middle school. The thing is that this relationship was established in Greece. It bears the name of the Greek mathematician, Pythagoras, who was in the 6th century BC. But it was also independently developed 200 years before that in India, actually. And it seems like the Babylonians understood this idea without formalizing it in the same words 1,000 years before that. So it's a very old idea. And it turns out to be one of the most useful ideas of all time because it can allow you to extrapolate meaningful information from a smaller set of information, especially spatial information, right? Humans are spatial entities too. This is something that I feel like could be better processed in the astronomy community. Everything that we do is based on sight and topography, right? It's funny because if you think about it, this is so baked into our brains that we can't even talk about things without using visual metaphors, right? If you explain an idea to me, I'll say, I see, right? Or I'll say, oh, that's a bright idea. Or I'll be like, this is illuminating, right? All of these ways in which we think are fundamentally visual. They're based on spatial representation. This is just how humans are. And I don't think it's an accident. I think that really tells us something about the physical universe that we're trying to explain. So here it is. This is really the best way of understanding the Pythagorean theorem, which is going to matter when we talk about parallax in a minute. If you take 3 squares, if you take 2 small squares, and you put them at a right angle to each other like this, then the square that's made at the hypotenuse is going to be equal to the area of the other 2. If you combine these 2, you're going to have the same area as this one. Simple realization. I have no idea how these people happened upon it, but once you know this, you can come up with this very simple a squared plus b squared equals c squared relationship. And that's going to be the key to determining how far it is to these stars, right? Because what we can do is we can set up that base of the triangle, and we can know the distance, whatever it is. In our case, we'll talk about it more in a minute, but it's essentially the radius of the orbit of the Earth. And once we set that up, then we can actually narrow in on that angle. All we need to do is come up with the angle that we're measuring, that we're observing, that difference there. And so this turns out to be supremely useful. Before we get there, we have to talk a little bit about what a distance is, because astronomers have some really interesting and strange ways of measuring distance. And, how did people measure distances originally, right? Where did these unit structures come up from? It's actually kind of intriguing. So the first ideas were basically based on parts of our own body, right? Like the knuckle. For instance, I believe that the inch came from the knuckle, or the thumb knuckle. The hand, the foot, we still hear those, right? And so, it hasn't always been based on tens, but we have 10 fingers and 10 toes, right? So that makes a lot of sense that we count in units of 10. The Babylonians counted in units of 60 and sixes. And why is that? Well, that's a little more puzzling. There's some different theories about it, but you have 3 different knuckles on your fingers, or 3 different bones, I guess. I'm not an anatomist, but you have 3 different. What are these things called? Somebody. I think the phalange is the whole finger. Anybody? Anyways, knuckle. Well, the knuckle is in between the 2 things. Bones. I don't know. Anyways, you got 3 little. Right. We're in astronomy, exactly. You got 3 little pieces finger, right? So maybe since you had 3 of them, then you can add up, then you'd have some units on your hand. You could get to some 6 out of that. I don't know. I'm not totally convinced of any of these theories. But the Babylonians used 60 for whatever reason, which is quite interesting. But all of them set up spatial dimensions on a coordinate system that had 3 axes which are 90 degrees orthogonally oriented to one another. This is critical. So the easy, most simplified way, you can use as many axes as you want, but you can't get away with using less than 3 to describe the spatial volumes in which we all operate and exist in. And this is length, width, and height. And so if you want to figure out a place on a map, you only need 2 dimensions, right? But if you want to figure out a place in reality, you also have to understand the height. Are you up in an airplane or are you on the ground, right? And this matters, of course, more than ever once we leave our planet, because we can, kind of simplify the surface of our planet in two of these different dimensions. But when we get out into the cold, vast regions of outer space, then we find ourselves needing the 3 of them. And so we set up a coordinate system for determining that. I guess what I'm trying to get across to you guys is that the word space is essentially describing place, right? It's a coordinate system that describes place. So, one of my pet peeves is the idea that you could exist in space, because space is not a thing that you can be in, right? It's not a substance. It's actually just a void. It's an empty place, or it's a place, right? So can you be in a place? I guess so, but it's tricky because you don't want to start confusing it with an actual substance of material, right? It's just a coordinate system at which you have a location within. So at some point, I think it was the French, decided that they were going to standardize distances for everybody. So instead of saying that, this is 20 knuckles long or whatever, then it's like, well, whose knuckle are you talking about? You get into all sorts of issues. So the French standardized this concept. This was during the Napoleonic reign. But of course, the history of France is absolutely fascinating. They were the first democratic revolution that ever happened, and that's, the fallout of that is all still playing out. And they set up this kind of ingenious system, and what they did was they essentially defined the meter by the length of 1/1,000,000th of the length of the arc of the Earth's surface from the equator to the North Pole. And so that's what a meter is, and it's still what a meter is, which is very strange because you have to ask yourself, well, how did they know how long the arc was from the North Pole to the South Pole? From the equator to the North Pole. And that is a story that we told last semester, but just to give you a simple explanation for it, this is actually determined way back in the Greek eras, a couple thousands of years ago. And the essential idea was that, hey, the sun is so far away that its rays are coming in essentially parallel to one another. And so if we look at the shadows that are cast at 2 different points along some particular latitude line, then what we can do is we can deduce the angle backwards, right? Because remember, when you have parallel lines, the interior angles are equal. This is taking you guys all the way back to 8th grade algebra or something, or 8th grade geometry. So what you do is you can determine those interior angles, and that gives you the angle of that arc from the center of the Earth. And if you know the distance that you walked between the 2 poles that you were measuring the shadow of, then you can extrapolate that arc all the way out to the radius to the circumference of the Earth. And they turned out to be astonishingly accurate, as far as we can tell. Again, they didn't have the meter back then, so they were using units of stadia at the time, which was a popular measure. And there's still debate about what exactly a stadia is. But it seems like they were in the ballpark, at least. The calculation is solid. It's a reasonable way of estimating the size of the Earth. So there you go. So the French took this and they used it to standardize the meter. Right around the same time, they also standardized the kilogram, which is interesting. That's the unit of weight, which is essentially how much a liter of water weighs. And it's very much still the same today as it was back then, right? We've changed the definition of the meter a few times since then. And it's kind of perplexing why that would be, but they tried to essentially set it up as the wavelength of a vibration of a particular atom back in the 60s. So remember, we've talked a little bit about how light is generated, but needless to say, atoms are always breathing, right? Their surfaces are always expanding and contracting, which is something quite beautiful to think about. And this is what essentially propels them and allows them to give off light, it seems like, right? There's this concept of quantum jump where they jump energy states. Let's say they expand, and then they contract and they give off light. They relax into the network, and they give off these waves of light. And we'll play with what that really means in a second. So people standardized it by the wavelength of this particular atomic transition, which was actually in krypton, 86. And then 20 years later, they did it again, and they decided that, no, we'll standardize it by the distance that light travels in a meter on Earth. They'll standardize it based on the speed of light in a vacuum, not by how much it travels in a meter. So all of these things give very congruent measurements. The question is, how standard are they, right? And again, all these measurements are set up on Earth. So if there's anything else playing into the variables, they're gonna matter. I think that's what went wrong with the atomic vibration experiment and why light makes a better ruler. If you take an atom that's vibrating, like say this krypton atom, and you move it away from the Earth, it turns out that it actually vibrates faster, which is makes it not the best clock for standardizing things. And we'll talk about why that is later. There's, of course, the general relativity description of how that happens. But if you think about it just intuitively, if you're crushing something with gravity, it's going to be under a lot of stress, and it's not going to vibrate as fast. So light in a vacuum seems to travel the same speed no matter where you are. And so that probably makes a much better ruler. There's some argument given for light interacting with gravity, but not at the scales of Earth. We actually only observe it in very specific contexts, particularly in the limb of the sun. Yeah?
Just about to ask, can the speed of light, can light itself be accelerated, say it gets flung around by a black hole?
Yeah, so I'm not sure how much I want to get into that right now. Yeah, I think that, so one of the central postulates of the special theory of relativity is that light is the same for all observers in every context, right? Now, the mathematicians have ways around that, and there's different velocity addition formulas, and they'll try to say, no, we're talking about like I said with the Doppler effect. Oh, you're just encountering more frequent waves or something like that. So the standard answer would be no, but there's contortions around that as well. Now, there's also this argument that light is affected by gravity. This is the central tenet of Einstein's experiment. And this is tricky because, we're gonna do a whole lecture on this, so I don't want to totally, but I do want to say that the places where this effect has been measured, especially where it was first popularized, was during an eclipse in the limb right at the edge of the sun, essentially. And this is kind of perplexing because if gravity was affecting light, you would expect it to fall off with an inverse square law. It should be affecting it at every distance but a little bit. In other words, you would expect to see these little rings around all of the stars in the sky. So I'm not particularly convinced of this postulate yet myself. Anyways, we'll give it the due process it deserves when we get there. Okay. But yeah, light goes extremely fast, 300 million meters in just a second. So that's how we define the meter most recently. Now, there's a couple of ways that we're not really going to get into today that people use to gauge distances in astronomy. And I do want to mention them at least. This is one of them. It's called an interferometer. And maybe, I don't know, maybe we'll get to it later in the textbook. I haven't looked yet. But I'm pretty sure that we won't, because generally speaking, interferometry is used for, it's often used at the small scale to look at very tiny things. And the basic idea is that, my screen's not working. The basic idea is kind of shown here for two telescopes, that if you understand the separation distance, the waves are going to reach the two antennae with a slight delay here. And the delay is going to result in different phases of the light, right? Some of them are going to be, one radar dish is going to be getting a peak when another one's getting a trough. And you might ask, what does that actually mean for interference to happen? And I do want to talk about that. The other way that they'll use is radar. So particularly with the planets that are very close to us, you can literally just do what the cops do on the highway and shine a light which reflects back. And again, you're looking at how that speed has been mitigated by the reflection, right? And it's a very similar idea to the Doppler effect that we talked about before, where you're encountering more waves per unit time. Okay, so what about this interference stuff, though? I think this is really worth taking a second to explain, because this is, potentially one of the most ill-conceived ideas in all of physics. And so it's worth just settling the score on it very briefly, because interference is going to play an important role in understanding how waves interact with one another. So, have any of you guys ever, anybody own any of those noise-canceling headphones? Right? Okay, cool. Like everybody. I gotta get a pair of those. All right, so how do those work? Anybody? So what they do is they sample the sound in the environment, and they process it and give it back to you in a very interesting and particular way. So what is sound, right? It's waves of pressure, so atoms hitting some membrane, like your face, your ears, and then there's relaxations in between, right? And so what does a speaker do? Well, it pushes out the air, and then it relaxes, right? There's a head on the speaker that's going like this and pushing and relaxing. So what the noise-canceling headphones do is they sample the sound in your environment, and they play relaxations where there's supposed to be pushes. So you get cancellation of the actual noise in the environment because it's getting played back to you opposite, which is take a minute just to think about that. And this is the concept of interference. This is perfect interference. You're taking the exact same pulse relax system, and you're putting the relaxation waves where the push waves should be, and you're canceling it perfectly. Now, this is the same thing that is happening in light. We have the same principle that is available to us. And it's absolutely perplexing to people because light is understood to be a quantized property, right? Light travels in waves and interferes like this. It's like there's a push and a relaxation that are interfering with one another, but it also happens discretely. And so how does this happen? Well, clearly the structures that are conveying the light are discrete, right? So that you can have a deformation in one particular ray of light that doesn't affect another ray of light. Now, that hasn't really been worked out because people aren't concerning themselves with the material basis of how this works anymore, although they were desperately trying to figure it out back in the late 1800s. So in a sense, what happens when you get these interference patterns is that those atoms at the back on the detector are getting mixed signals, right? Some places they're getting combined pushes of light, and some places they're getting told to push while they're getting told to relax at the same time, and you get these dark bands on it. And the particulars really of how you skew those sources from one another, or how you move the baseline where you're detecting it, can give you information about the distance. So that's something to remember. I think that we might look more into cosmological interferometers later because they're quite useful for extremely large distances as well. So when we get to cosmology, we'll deal with this more. Any questions about this? Light. All right, so let's get back to our discussion of parallax. So this is the basic setup for a surveyor. Do any of you guys have surveyors in your family? Anybody? It's kind of a cool job. So people go out and they mark out the distances to different things, and they have to lay these out if you're building, you know, a new structure or train tracks or anything. You have to figure out how to map your drawing onto the real world. And so they'll set up all these pegs and everything. Well, mark this out to 400 meters and all of that. How do they do it? Well, they do it the same way the astronomers do it, right? They'll have a known baseline, so they set up this triangle really nicely. And as you can see, it's essentially two right triangles, so this gives us our nice Pythagorean situation. And what they'll do is they can measure the angle at which they will focus on a distant object, because you know, that angle is going to change depending on how far your baseline is. And from that, you can do the basic trigonometry and determine the distance. Super useful, also super ancient, right? The Greeks were doing this. This is not a new idea. And so naturally, it makes sense that people you know, would apply this to astronomy. And you can experience this yourself, right? I think everybody here has two eyes. And so you might ask yourself, why do we have two eyes instead of one? Well, you know, of course, two is always better than one, but why don't we have like three eyes or something? It comes down to essentially establishing this baseline because we want something called depth perception, right? You want to be able to reach out and touch something. Now, I don't know if you guys ever been to the eye doctor or anything and you've tried to spend like a day with one of your eyes covered. Maybe you've just done it for fun or something. Pirate dress up Halloween in 5th grade or something. It's very difficult, actually. You know, it's fine. You feel okay for a few minutes, but after a while, you'll find yourself, you know, missing steps and grabbing like not picking up the cup that you reach for and things like this. And of course, people can train and adapt to it over time. But essentially, what you've done with your face is set up a baseline, which is really nice. And so this is great, but you know, the focus of that triangle is largely established by the distance that you have available to you on your face. If you want to look at something farther away than like a city block or something, then that base of that triangle is not really appropriate anymore. And so you really have to do kind of what the surveyor does and actually move to a new location. So setting up these wide baselines is kind of the key to everything, really, in astronomy. And I just want to say anything about that. Yeah, exactly. So the wider that baseline is, the further away that you can really make the further you can precisely make statements about something that's far away, right? If you look at things that are really far away to you right now, you might be like, yeah, there's something over there, but you don't have a great deal of resolution about it, right? And we ultimately want to make really, really crazy statements about things that are unbelievably far away. Like really, we want to be able to say precise statements about things that are unimaginably far away, like distance scales that are just inconceivable in our human world. So good news is we have this actually, and this has been known about for a while, that the Earth, since we essentially conceived of it as traveling around the sun, we realized we had those two eyeballs, one at each side of the orbit, right? So in any two oppositional seasons, you're going to have the potential to set up a baseline, say in the spring or the fall. You're going to be able to look at a star from a different location, right? And this is how we do it. So, you know, this is way simpler quantitative relationship. This will be useful to you guys on the quiz. It's in your textbook, so don't worry about it. But the cool thing is that with just a little bit of this basic Pythagorean trigonometry, you're able to pull out this relationship where your distance is equal to 1 over the parallax separation, right? This is really cool. So as this orbit gives us a baseline of something like 300 million kilometers, and that's also 2 times the distance of us to the sun, which makes sense. So 2 astronomical units. You know, this seems like it would be perfect, but there's problems with it. Actually, visually speaking, when you try to see the parallax of the stars, you can't see them. And so the Greeks, even actually much later than the Greeks, there was this huge argument going on about whether the Earth was at the center of the universe or the sun was, right? Very famous, one of the most famous scientific debates of all time. And the argument given by the geocentrists was, hey, if that's the case, why can't we see any of this stellar parallax stuff? Because they were looking for it. They had telescopes. And, well, they had did they have telescopes? I might have to walk back on that. They either had just gotten primitive telescopes or they had no telescopes. But they couldn't see the parallax, and they couldn't measure it. And I think that was, that all started to turn around when people started building more and more powerful telescopes. Because when you got really, really powerful telescopes, then they were able to see something might be going on there. And that kind of sealed the deal for the heliocentrists. Another thing that's worth remembering, I think this comes up in one of your quiz questions too, is that the parallax angle itself, the angle of separation that you measure there, is in some sense proportional to the volume that you're going to be surveying. And this makes sense. As your baseline opens up, you're going to be reaching into a bigger baseline. So that's something to keep in mind. It's proportional, in fact, to the radius of that baseline squared. And so you're going to be seeing a bigger region of space if you get a bigger baseline. And this is important. And we'll talk about how to improve those baselines. So how do we measure it? Well, the parallax itself, this is the angle of separation here, is actually measured in something which is called a fraction of an arc, right? We'll call it, once they measure them, by the way, they use the Babylonian system of sixes, back to that again for some reason, to divide up the circle, right? And so the circle is divided into minutes and seconds, which are all units 60. And so a second of arc, we call it an arc second, is an angle of 1/360 hundredths of a degree. Okay, this is a really, really tiny amount. And so, like, I think your textbook gives the example that if you took a quarter, like a little, people even use quarters anymore? Maybe for washing machines. So if you took a quarter and you put it 3 miles away, you would be viewing it to have a diameter of 1 arc second if you used this measurement system. So, people didn't really start taking these measurements until the early 1800s. This is when they had the decent enough telescopes to actually pull this off. And it turned out like even the closest star to us, which is Alpha Centauri, only had a 1.5 arc second diameter, right? So it's very close to that idea of a quarter at 3 miles away. Really, really far away. Really, really far away. And so one of the ways that we talk about, one of the ways astronomers shorthand distances is by just listing this parallax. And they do this with this concept of parsec. So let's see here. The question that they asked and the way they came up with this parsec thing was they said, how far would a star have to be to have a parallax of exactly 1 arc second? And this is how they defined it. So the answer is about 3.26 light years, or about 3.1 times 10 to the 13th kilometers. So 31 trillion kilometers away, right? That is 1 parsec. And you can understand why they just kind of threw in the towel on the meters when you get into the trillions of meters. It's just sort of pointless. And it's easier for them because the parallax is actually what they're directly measuring. So a star with a parallax of 1/10 of an arc second is found at a distance of 10 parsecs. One with 1/20th of an arc second is 20 parsecs away. Okay, this is the basic distance relationship that you see on the board there for parsecs. Okay, so this equation is going to give you the distance in parsecs. And just review again. A parsec is 3.3, 3.2 light years away. It's a really, really far distance. So no star other than our own sun is even within a parsec of the Earth. the nearest neighbors to us are in the constellation Centaurus. And the brightest of these, like we said, is Alpha Centauri. Now, Alpha Centauri is actually a binary star, which is cool. And we talked about those last week, or last lecture. But those stars are 4.4 light years away from us. There's another third star there, which is about 4.3 years away, called Proxima Centauri. Now, Proxima Centauri is interesting because it's one of those super common stars, more common than our star. It's a red dwarf, right? This is something like anywhere between 75 and more % of the stars in the galaxy. And let's see, like the nearest star that you can actually see without a telescope turns out to be Sirius, which is actually 8 light years away. It's also in a binary system, and it's got a white dwarf with a bluish-white main sequence star. And so that's kind of interesting. So the closest visible star that you have is 8 light years away, and the sun's light is 8 minutes away. That's maybe something that you can keep in the back of your head in terms of gauging these distances. Okay. So let's talk about this a little bit. So people started bringing in stellar parallax measurements. This is actually a map which corresponds similar to the HR diagram that we talked about before. They have the stellar parallax and hence the distances for all of these different stars, which is quite interesting. And they did these parallax measurements by putting a satellite out here at L2. So I want to take just a moment to explain the Lagrange points to you. This is kind of cool space trivia, but it's actually quite important technologically. So anytime that you have one body orbiting another, you have the appearance of these very stable points in that orbit. It's interesting because, and we call these Lagrange points. What's interesting is that and every pair of systems is going to have this. So I'm talking about the Earth-Sun system, but we could also talk about the Jupiter-Sun system as well. And what's interesting is that in the Jupiter-Sun system, you actually find a ton of asteroids orbiting in the L5 region and a bunch more orbiting in the L4 region. These just happen to be places where the gravitational interactions of each of those bodies equals out and balances. And so there's one for us on the other side, away from the sun. These are beyond the moon. And there's one on the interior between the moon and the sun. And those are the two most useful ones for us as scientists, because we can plop our satellites out there and they'll just stay put, essentially, right? So this is really useful because then we can all of a sudden put a telescope on that thing and it will just follow us around our orbit. We don't have to put any rockets on it or anything like that. It'll just stay put and we can make these very careful parallax measurements at different sides of the orbit, which is cool. So the first version of this was put in space in '89. This was called Hipparcos, and that measured a bunch of stars, like in the thousands, to a distance of out to 300 light years away, with a pretty decent accuracy in the 10 to 20% range. They actually replaced this with a new satellite called Gaia in 2013, which actually expanded the reach incredibly. I think it just had better sensors. And it was able to actually catalog something like 1 billion stars with an accuracy within a few millionths of an arc second, right? Remember, an arc second is a 3600th of a minute. This is just unimaginable precision, right? We're talking about like pixels at this point. So, this scatter plot's quite interesting. And, people begin to actually start to consider how the distances to these stars mapped really nicely with some of the other characteristics we were talking about before, right? The masses and the luminosities. And we'll get back to that at the end of the lecture, but it turns out to be there's a very nice correlation between these things, which is nice because it allows us to extrapolate maybe the in-between stars that we can't quite get to. We can see something about them, but we can't see everything. And so we'll get back to that relationship a little bit. Questions about the Lagrange points? All right. Let's talk variable stars. Last time we talked about using binary stars to determine luminosity. But what about distances to stars that are really far away, or they're not binaries, or they're in other galaxies? And it turns out that there is a more broad class of stars. We call them variable stars, which we can use as clocks, essentially. And clocks, which have a predictable period to them, then we know essentially what we're looking at, and we can compare it to something that's nearby us, and we'll be able to get a distance as a result of that. Now, variable stars is any star which changes its brightness with some periodic regularity. So actually, the ones we talked about last time, these binary systems are a kind of variable star, right? But they're not really thought of that way anymore so much, because we understand they're two stars and they're eclipsing each other, and there's this whole other thing going on. Another way that you could have a variable star that wasn't what I'm about to talk about is, say, some dust was being emitted, right? If there was some, sometimes stars can be eruptive. I hope we'll have more time to talk about. I think we'll talk about the deaths of stars and all the different ways that stars fall apart at the end of their lives, at least in theory. And one of the ways they do that is they'll periodically eject some outer portion of their material. And as they do that, it can actually dim the appearance of the star. So that's another kind of variable star. But that's not the clock that we're going to be talking about today. The clocks that we're going to be talking about today are these two particular types. There's these two breeds of stars that are very predictable. They have a very predictable light curve. This is a light curve, how bright it is with respect to time. The time that it takes to fall off, the shape of that curve is what really allows us to dial this in. And the two we're going to talk about are called Cepheids and RR Lyra, which are the two main pulsating stars for making these clocks and these distance maps from. Now, we can measure the pulsing of that using the Doppler effect, right? As it expands, it's not just getting brighter. Also, there's an associated blue shift as it expands and an associated red shift as the surface recedes. So this tells us that there's something actually physically going on at the surface of the star. It's actually breathing, much like the way that I conceive of the atom. These things are actually breathing, and that changes lots of things. And, there's more to that story. There's a real question of what's going on inside of those stars as they're doing that. And, the other thing, their temperature changes as they're breathing too, right? This makes sense because they're coming in, there's more pressure, it's getting hotter, there's something going on. And the particulars of what drives that process are a little bit beyond the scope of this course, but I think that it's worth maybe talking about two potential ideas. Because actually you would think this is a rare occasion, but actually something like 2/3 of the stars that we can actually see are pulsating. I'm sorry, 2/3 of all the variable stars are in this pulsating category. So why do they do that? Well, it kind of takes us back to Eddington. So Eddington had this explanation which was essentially based on the expansion and contraction of a gas. Basically the idea that, as it swells, its outer layers expand and this cools them off. And then because the decreasing temperature, there's also that the gas is able to, its ionization interactions change. So it's not able to participate in light the same way. This Eddington claims makes the gas more transparent, and then it's able to radiate away the energy easier. And as it does that, as it lets out all this radiation, it starts to contract again. And then as it's compressed, it's heated, and then this whole cycle repeats. This is tricky for me because it depends on the idea that you can make a gas opaque by compressing it. And like I said, we've never actually seen this on Earth before. And so I'm not totally satisfied. But one thing that's really interesting to me, if we start to treat plasmas more like liquids, we actually have a mechanism here because, when you actually add pressure to a system on that phase diagram, right? Remember, all matter exists in different phases, right? It can, as you cool or as you squeeze it, it's going to transition from something that's solid-like to liquid-like to gas-like. And then there's all these exotic phases too, right? But what's really interesting is that you actually have phase transitions in something that's more of like a liquid metallic structure where you can actually get different arrangements of that lattice structure and you can get different kinds of light that come out of it. Which makes sense. If you change like a light bulb's filament and you put a different kind of filament in it, you're going to get a different kind of light quality out of it as well. So, you know, that debate's still going on. Maybe that will be a huge paradigm shift in the future. But for whatever reason, these things change color, they change brightness, and their surface is expanding and contracting, which is very interesting. Let's talk about the Cephids first. So, you know, most of the Cephids are seen here when we look towards the center of our own galaxy. These are these big, fat, yellow, pulsating stars. And the reason that we call them Cephids is they were found in the constellation, or in the group, the zodiac group, Delta Cephei, which is interesting because it just stuck. You know, we find them all over the place. But again, the conventions, whoever writes that first paper and identifies it, it tends to stick around. So even though there's Cephids in all sorts of places and other galaxies, we still give it this name based on its first location in this first star group. It turns out also that when we put them on the HR diagram, the Cephids cluster in one particular place. So you can see here that the Cephids are separated out on this stream in this transition, right? Now, you're probably starting to put together a little bit of a story, right? If stars are spending most of their time on this main sequence, then they're going to pop out into one of these other two groups at the end of their life. It's interesting because the Cephids seem to represent a sort of transition phase, right? Which is, I think, is why people believe that this pulsation is something like an end-of-life story for a star, right? There's something changing in them all of a sudden that puts them drifting towards what we would consider a kind of standard second-to-last step for a star, which is ending up as a giant star over there. And don't worry too much about those stories. We'll get to them. We need to make sure that we understand how we get all the variables first. But you can start to see a picture emerging a little bit. What's interesting is that the R Lyra are another group of these, and they're very fast period, like less than a day, in terms of how fast they're breathing. Right? This is pretty crazy. And they can usually double, somewhere in the order of doubling their brightness during this contraction phase. And they find that they kind of cluster into a region that has all about the same brightness, right? This is the luminosity over here, absolute magnitude of luminosity. So they're all about the same power. And they all also seem to cluster, at least these original ones that were determined, were clustering all at about the same distance, which was interesting. So in this sense, the Lyra make a really good standard candle. If we characterize them really well in our own galaxy, we know the distance to them, then we're able to say, if we see one in another galaxy, how far away that is too. That's the idea, right? And it's really important, guys, to remember that these assumptions that we make are open to criticism and revision in the future. There's a lot of these fundamental ideas like, hey, if things are happening over here in our galaxy and we see something similar in that galaxy, it's probably the same thing. But it might not be, is the truth of the matter. And actually, well, I'll get to this in a second, but there are some problems with actually extrapolating out the distances from these. But let's review how we do that. So this is our big equation for today regarding pulling out the distance from these things. So I don't think that you'll need this one for any of your assignments, but I do want you to be aware of it. So this is essentially going to allow us to read off exactly how bright something is from how apparently bright it is. And the idea here is that the apparent flux F, right, this is what it seems to be, can be related to the actual luminosity L by the distance. And so what we do is we compare that intrinsic brightness with the actual brightness. And this is going to allow them to calculate the distance. So remember, they know from other measurements, they're able to know the distance to these particular forms of pulsating stars. If they see them somewhere else, then they're going to be able to extrapolate the same thing backwards and to scale it. And this is called well, that's not necessary for you guys. Now, like I said, there's some issues. So one of the problems is that depending on the composition of these pulsating stars, you could run into different measurements looking at the same type of star. So if we assume something that's pulsating with a particular landscape is the same as another one, it turns out that you can actually get different measurements, right? This turns out, people speculate that this is based on the metallicity of the cell, how much metal is there, which I think plays into the argument that I was making earlier, where perhaps it's smarter to really engage with the concept of metallicity in general with stars, because a plasma is essentially indistinguishable from a metal in terms of its conductive behavior, at least a certain kind of metal, generally speaking. And so this has been discussed a lot in the literature lately. Another issue is what band of light you look at, too. And this is particularly troubling because if you use different colors of light to watch these things, particularly people will use IR bands. They seem to be the most reliable. But oftentimes you get different distances depending on which color you're looking at. And the reason for that is maybe beyond, is still in heavily debated. Right? So these aren't perfect systems, but they seem to work more or less all right. And they give us what we feel is something in the range of a 10% confidence window. Now, 10% confidence with light years of distance is, would be completely unacceptable if we were measuring something here on Earth or trying to build a rocket that went somewhere, let's say. But at these scales, it seems to be okay. It seems to give us at least the general picture of what we want to know. So where do we go from here? Oops, I skipped one. Right. Now, there's another way of looking at parallax, which is different than actually just reading it off. And it's actually called spectroscopic parallax. Now, this is funny because spectroscopic parallax has nothing to do with parallax, actually. Again, I apologize on behalf of all astronomers everywhere. This is terrifying. But you have a chapter, a subsection in your book about spectroscopic parallax. And if you read about it, you will get terribly confused because you'll be like, what does this have to do with parallax? It has nothing to do with parallax, actually. I don't know how that one happened. I don't have the history for you on that. But the technique is actually to use spectroscopy, right, to separate out the colors. And what you do is you estimate the star's temperature and surface gravity as a result of that. And what that does is it allows you to peg it on the HR diagram. Oh, this is a dwarf star, this is a giant star, whatever it is. It allows you to get a rough idea of where it should sit on there. Excuse me. And then from there, you can actually pull off an estimate of the absolute luminosity and work backwards and so forth, right, to figure out your distance. So the concept of spectroscopic parallax is really a reach. In all honesty, it is essentially grouping something by its family members and then pulling them off. There's obvious problems with this. I don't know. I feel a little ashamed about it, honestly. It's kind of like saying, oh, well, you're tall, so you come from a tall family or something. It's just, it doesn't play out that way. We know there's a lot more to it. And you got to understand that people are really, especially the planetary scientists, but I think the astrophysicists are next, people are really starting to apply the concepts that Darwin came up with about biology and evolution to things that are outside of the Earth that are evolving as well. Planets are obviously starting to do it. We can actually watch planetary systems forming, and they're doing some really cool evolutionary processes. The stars are almost certainly the same way. They're going to be a product of their environment. Everything is, right? No matter what you're talking about, if you're trying to make an explanation for why something looks the way it does, don't just fixate on the object itself. Look at what's happening around it, right? And I think that this is the next step that's really going to fine-tune our understanding of these groups and why they relate to each other. Because right now, we've essentially set up something like a family tree for these things. Yeah? Yeah, of course. No, I just mean that like this idea of natural selection. All right, so if you forget about heredity for a second, but you just apply selection principles to any natural system, you can evolve it, right? So people are working on all sorts of really cool models of trying to get computer systems to evolve as well, right? If you give some minimum input to it and you confine it to some circumstances, can you evolve small groups of can you evolve a computer program? Can you evolve small groups of cells? You know, I talked to this really interesting dude last week who's in Australia, and he actually is training these little dishes of neurons to play Pong. It's crazy. You guys know Pong? It's like this old-fashioned video game, like one of the first video games where you basically, what's that? It was the first? Okay. Yeah, I did not have an Atari as a kid, sadly. But you move this stick around, and they reward the cells, right? This is the reinforcement aspect, right? The cells are rewarded with a predictable pulse of electricity when they hit the ball, right? When they organize themselves so as to make the electrode, move the stick, the panel, whatever you want to call it, in the right direction, the cells are rewarded by getting more of the same. But if they miss the ball, they punish it by giving it chaotic pulses of electricity, right? And so for whatever reason, the cells don't like chaos. They like to have this predictable rhythm of electricity being supplied to them. So if you figure out the motivational structures that are at play, and I think this is kind of what's happening too. It's easier to see in planetary science for whatever reason. I don't think that it's made it into astrophysics yet, quite. And I think it's going to totally upend the way that we look at things, because if you think about the way each one of these things evolved, the first thing we did in planetary science was we laid out all the characteristics. Okay, there's these kind of planets, there's these kind of planets. They're kind of in a family together. They kind of have shared characteristics. Okay, there's these moon things. They're kind of similar. You know, like if you took my class last semester, it got kind of ridiculous. Like we're just going through the moons. It was like, oh my God, not another lecture about moons. Because it was just like, they're all clustering into these categories, right? But what's cool is that people just in the last like 5 or 10 years, I mean, this is literally the cutting edge of what's happening, is people are realizing that those planetary types can evolve from one into another. This is just being hinted at, right? People are kind of scared to talk about this almost. But there are some papers showing up, right? These Neptune-like planets, maybe they're losing their atmosphere. They're becoming something that looks maybe more like a moon or more like an Earth-like type thing. The Jupiters are close to the stars. Their atmospheres are getting cooked off. They're turning into something else. Like there's processes specified by their environment, their location with respect to the star, their temperature, their composition, the composition of the immediate region in which they formed. All these things are starting to come into play into the story of the planets. And so I certainly think those are going to come into play when we talk about the formation and the lives and deaths of the stars. But we're not totally there yet, is the thing. We're still in this cataloging phase, which is, you know, if this feels like we're cataloging stars, that's kind of what's happening, because that's where we're at with it. So spectroscopic parallax is truly just putting somebody on a family tree and trying to infer something about their characteristics as a result of it. No real shame there, but that, you know, it's worth being honest about what's happening. So we can also divide these things up on the HR diagram by their luminosity families too. So they give them these Roman numerals with a subscript Latin ABC. And so you have like 1As are the brightest supergiants, then they get down to the less supergiants, the bright giants, the giants, subgiants, and then by Roman numeral 5, you're down to the main sequence stars. So, you know, once you have the spectral class and the luminosity, you can position these things pretty well. And if we know how luminous a star is, and then we know how dim it looks, then the difference will allow us to calculate the distance. And that's kind of what this whole project has been about up to this point. So let's just review those really quickly. So this trigonometric parallax is being done with Gaia. This is actually quite successful. I assume they're going to launch a new one as soon as they get done with this. It'll probably be able to reach even further and establish more precision. And so we also have the Lyra stars. They can reach out to 300,000 light years. That will not get us to another galaxy. The Cephids are interesting. They're reaching much further, 60 million light years, and then which will actually accomplish what we need it to do. And then the HR diagram is honestly what we're using for some of the more distant ones, right? We're actually just trying to say, okay, this star in this galaxy over here looks like one of our stars over here, and so we'll put it over. We'll say it has this distance. Measuring these really, really far distances is not impossible, but it is very close to. So, again, what is the point of all of this? The point of all of this is if we combine the distances for the stars and we combine it with their composition, their luminosity, the temperature, with all these techniques that we've done this week in a sort of blizzard onslaught of technical information, we're going to be able to work towards a story of how these things evolve, how they live, how they die. If we can apply the concepts of life and death to them, it's easier for us to understand. Why does it matter? Right? I mean, this is an interesting question. I think that astronomers get a lot. Like, who cares? And of course, there's a practical survivability aspect to it. Like, okay, yeah, we have a star. We should understand where it's headed in the future so we can be prepared for it. But I think there's something more going on here, which is that, again, humans since time immemorial have tried to put some order onto the chaos that's the universe. Without it, it's complete madness, right? It's literally the hallmark of psychopathy to not be able to order your surroundings. If you think about the complete disintegration of the mind in the case of like extreme schizophrenia, there's no ability to take information and put it in the proper place where it can be utilized. And I think what we're fundamentally trying to do here as astronomers is a human project as well, which is really about putting a story on the world that we find ourselves in. We wake up, we're here, we're alive all of a sudden. What is this place? What's going on? What are these orbs that are flying over our heads? And I think that it's more important than the technological project. I think that it's really important for us to understand the point of this and to understand what we should do and how we should behave ourselves within it. And so we'll talk more about that as we go forth. And I think what we'll do when we get to the actual stories of the stars is we'll try to contrast it with the stories of the stars that people have told since antiquity to some extent, because that gets into some really interesting territory about how we should actually behave in relation to these things, what they can teach us about our lives on Earth, which I think is it's not insignificant. It's not just a silly superstition. There's actually a lot of really valuable wisdom there that we could use. Otherwise, you guys have a great weekend, and I'll see you all on Tuesday.